morning. Let's take a look at Bronco the Skydiver, make sure you understand what's going on. First of all, this is all about Newton's first and second law. We have Newton's first law is an object in motion stays in motion. An object at rest stays at rest. This is never going to be at rest and after it jumps out. So it's always an object that stays in motion, so that you will see some dynamic equilibrium. But most of the time, I wouldn't say most of the time, maybe half the time, it's actually doing Newton's second law. Newton's second law is actually this right here, which is acceleration is the net force over the mass. And so in each scenario, we can take the net force and we take a look at it. So what we have here in this one is the resistance is 0 because he just jumped. So there's no resistance, there's no air resistance. He's just jumped out. And so his weight is acting down alone with 1,000 newtons. And so acceleration is always going to be the net force, which in this case is 1,000 down over the mass. And the mass is going to always, in this case, be 100. And so the acceleration here equals down 10, and that's meters per second squared. And it makes sense because when you have no wind resistance, you should fall with free fall. And if we did this with 9.8, like, if we did this with G equals 9.8, then we would get 9.8. But in this case, let's use G equals 10. In that way, it makes the numbers a little easier. So in the next one, what we have is we have the net force on the next one, and I'll do that maybe in a different color. Maybe I'll do it in blue, is we have 400 resistance. And so this next one, we have 400 resistance. And then down, we still have 1,000. So the net force is going to be 1,000 minus 400. And then, of course, over 100. And 1,000 minus 400 is 600. And 600 over 100 is 6. And so we're still accelerating down with 6 meters per second squared. We're just not accelerating quite as much as before. So if our acceleration is here is down, and our acceleration here is also still down at 6 meters per second squared. So we're accelerating, but we're just not accelerating as much as before because we're building up some air resistance due to our shape of falling through the air. In the next one, actually, we've gone so fast that we've gone so fast. Where did that go? Why is that there? That should not be there. We've gone so fast, and maybe I'll go to pink this time, that the up is 1,000 and the down is also 1,000. And so 1,000 over 1,000 means our net force is 0. So since our net force is 0, we are not going to accelerate. So here we are not accelerating, and this is an instance which we call terminal velocity. This terminal velocity will be about 200 miles an hour. You've basically, that doesn't look very good, does it? Stop it. Do I have an eraser? I don't know if I have an eraser. I don't have an eraser. What have my eraser? Clear. Whatever. Okay. Where the heck did that razor go? I have an eraser right there. Anyways, in that scenario, this one here, it's going about 200 miles per hour, and it's not going to speed up or slow down because the net force is basically 0 over 100, gives you acceleration of 0 meters per second squared. But you are moving down. Your velocity is down about 200 miles an hour. And what is that in meters per second? Actually, golly, I don't even remember what that is in meters per second, but it doesn't matter too much. It's fast. Let me go back to my there we go. Okay, so now as we continue on down the page, I'll choose a different color for this one. I don't know, purple. And so now the resistance is actually building up. I'm going to go like that. The resistance is actually building up. So now the resistance upward is 1,200. And so the downward is 1,000. And so this total net force is going to be 1,200 minus 1,000 over 100. And when you get is 1,200 minus 1,000 gives you 200 up. And 200 over 100 gives you 2 meters per second squared as your acceleration. and that acceleration is up. So now you're actually accelerating up. Now that doesn't mean you're moving up. It just means you're slowing down. So remember that when you're going down, your velocity is down. So I don't know, I'll put the velocity in green. So your velocity is down 200 miles an hour, right? So my velocity is down 200 miles an hour, but my acceleration is up. I've got the brakes on. The brakes aren't on full blast yet because the parachute is not out entirely. And so it's only got 1,200 newtons of resistive force. So now let's crank it up even farther, and let's do 2,000 newtons of resistance. And so what we have here is an upward force of 1,000. And so that's 1,000 over 100 equals 10 meters per second squared. Now you might think, okay, 10, it wasn't at 10 before, right? So this one before, this is 1,000 over 100, which gave me equals 10. But that was the acceleration was down. I was speeding up. I was going faster and faster and faster. Now the acceleration here is up. And so now I'm really slowing down. And I really want to slow down because I'm trying not to die. So now we'll slow down until we get to about 5 miles an hour. And so when this last one, this is about 5 miles per hour. And this is another form of terminal velocity, right? Terminal velocity says the net force, A equals F net over M. And what's the net force here? The net force here is 0. And the mass of the dude is still 100, but it doesn't really matter because 0 over 100 is 0. So he has 0 meters per second. Once again, that's his acceleration. This is the A. It doesn't mean he stopped moving. It just means that now he's going about 5 miles per hour. That's called terminal velocity. Okay, so let's look at the actual answers to the questions here. So I guess I'll go back and I will clear the whole thing and I will go back up. So the first question says, when Bronco's speed is the least, his acceleration is least or most. So when Bronco's speed is the least, that's this part right here. So when his speed is the least, his acceleration is actually the greatest because that was 10 meters per second. So that's really, he's going to accelerate a lot because he's got very little resistance. The faster you go, the more resistance you got. Number 2, in which position does Bronco experience a downward acceleration? So anytime the number below is bigger, then he's going to experience a downward acceleration. So it's just A and B. He's going to experience a downward acceleration because balanced or unbalanced, right? So balanced or unbalanced means that that's going to accelerate down, right? That's going to accelerate down, right? But is this going to accelerate down? No, he's moving down, but he's not going to accelerate down in that case. Okay, moving down the page. In which position does Bronco experience an upward acceleration? Once again, if it's like this, then that's an upward acceleration. So this one is bigger, and this one's also bigger. We're talking compared to the downward. Compared to the downward, this one is going to be basically 2 up, and this is going to be basically 10 up. So those two, it's an upward acceleration, and upward acceleration is going to be what's that? D and E. Okay, when Bronco experiences an upward acceleration, his velocity is still downward. I mean, come on, think about this. Is his velocity ever going up? Is he ever going back up into the air? No, he's slowing down. And in fact, actually, the reason that looks weird or it might be weird to you in some cases because whenever we're filming someone falling the parachute, when their parachute pops, they actually look like they're going up. But that's just because the camera's going down. The camera's going down. The camera's following them down. And as the parachute pops, it looks like they go up. They don't actually go up. They slow down so much that the camera has to go, oh, I got to go back up to them. So you're obviously never going back up. If you were super light, like if you were a mouse with a parachute and there was a lot of wind, you actually could go back up. But with a human, that would take an extreme amount of wind. So when Bronco experiences the upward acceleration, which is these two cases, his velocity is still downward. His velocity is down the whole way down. In which position is Bronco's velocity constant? So remember, constant velocity, it doesn't matter how big the arrow is. Who cares how big the arrows are as long as the arrows are balanced. And so as you look through here, there's a balance right there. I'm going to maybe put I don't know, let's go pink. And I'm going to go with this one. This one's balanced, pink. This one's balanced right there. And that's like that, right? And you go down the page, where to go. This one's also balanced, right? And it's the same thing. That's like that right there, balance. And so, in which position is Bronco's velocity constant? And that is F, and that is C. So constant C and F. Which position does Bronco experience a terminal velocity? And it's the same one, C and F. That's a terminal velocity. The difference is the terminal velocity in C is much greater, right? 200 miles an hour. Remember, there's going to go this one. The terminal velocity is the V, not the A, but the V equals about 200 mph. And then the V here, thank you so much for not allowing me to die when I hit the ground, is only 5 mph. Okay, if Bronco were heavier, his terminal velocity would be. Okay, so just imagine if you had the same parachute, but you had an elephant, right? So here's a nice, cute little elephant, right? And he's Elephant Drop is actually like a Disney movie of some sort. And so here's an elephant, and I'm not sure why I'm spending so much time on it. Here's the elephant, and the elephant has the same size parachute. Yeah, that elephant is gonna die. So, don't do that to your elephant. Um, if Bronco were heavier, his terminal velocity would be greater, right? And then you can compare that. If it was a mouse, his terminal velocity would be less. So the terminal velocity is basically a product of your shape, right? The parachute has this big open shape, but then also your weight. So you can picture the same thing. Like if I dropped a ping pong ball off the Empire State Building, right? If I dropped a ping pong ball at the Empire State Building, and then I dropped the same exact shape ball, like a lead weight, like let's say a fishing weight, the same exact shape and size of ping pong ball. Wow. I think you know that the ping pong ball would barely its terminal velocity would probably be like something like, I don't know, 25 miles an hour. But the lead ball would probably kill you, right? So that would be like a projectile that would be like shot out of a gun. It would not have a very much air resistance compared to its weight. So, anyways, the backside is the XVAF graphs, and that is covered on a different video. So that's the backside. That's a separate video. And anyways, there we go. Have a great day, and I'll see y'all later.